All right, sequences test review. I'm going to walk you through each and every single one of these questions. There are mainly two things to make note of. There are two types of sequences that we are going to discuss. There is what's known as the arithmetic, or some people pronounce arithmetic sequence, same thing. And that type of sequence is a pattern of numbers in which you're adding, or it could be subtracting, a common value every single time. The other type of sequence is geometric. Geometric is a sequence where you're multiplying by a number throughout the sequence. So let's look at our first few examples, and the question's just asking what is the next number in the sequence, but it's going to be helpful, of course, if we make note of whether it's an arithmetic sequence, one that's being a constant added value, or a geometric sequence, one that's being a common multiplied value. So looking at the first sequence, we have 2.0, 2.5, 3.0, 3.5. So this is a perfect example of an arithmetic sequence, because from one term to the next, can I zoom in a little bit more? Yeah, one term to the next, we are adding by 0.5, right? If I can make that look a little bit better. Not even close, but it's fine. Right? Every single time you're adding 0.5. So because we're adding a number here to get the next term, that is an arithmetic sequence. And now we're going to use that to predict the next term of the sequence. Well, if this pattern continues, if we add 0.5 again, then the next term in the sequence, right, the next number in the sequence, is going to be 4.0, because 3.5 plus 0.5 will make that next term be 4.0. So now let's look at the next sequence. The next sequence we have is 1.7, 2.1, 2.5, and 2.9. So the question is, what are we doing here? What is the pattern that I see? Now, it might not be too easy right off the top of your head to identify what's going on here, but if you want to test some theories, here's what you can do. If it's an arithmetic sequence, meaning that you're adding the same number here every single time, but we don't know what that number is. If you think it's an arithmetic sequence, or at least you want to try and guess that it is, well, what would happen is if you go backwards, right? If you take 2.9, for example, and subtract, because you're adding going this way. So if you go backwards, you can subtract. And you subtract the previous term before 2.9, so 2.9 minus 2.5, right? And we could just grab our calculator and we could type that in. 2.9 minus 2.5 equals, that's 0.4. Now, if I do that for the next one, if I try go backwards again from 2.5 to 2.1, and I do the exact same thing, 2.5 minus its previous term, which is 2.1. 2.5 minus 2.1, I get 0.4 again. And then one more time, just to check, right? 2.1 minus 1.7. 2.1 minus 1.7. And I get 0.4 again. So that's a good way to find out what that number is, the difference between them. So in this case, because they're all separated by 0.4, as we found out by going backwards, by taking the terms and subtracting them, I know that my common difference is 0.4, that we're technically adding 0.4 every time, right? And if you want to double check, you can. So start with 1.7, add that 0.4, and we get, oops, hold on, I forgot the decimal there. 1.7 plus 0.4, we get 2.1, right? And then if I take 2.1 and I add 0.4, I get 2.5, right? So it works, and you can double check with the calculator. So now that I know what I'm doing here, I'm adding the same number every time. Then if I add it one more time, right, plus 0.4, I'll get the next term. So 2.9 plus 0.4 is 3.3. So the next term would be 3.3. And that would be our answer. All right. So excuse me. So now looking at the third problem. So now looking at this 0.5 to 0.25 to 1.25 to 6.25, I'm noticing that this doesn't necessarily look like an arithmetic sequence. It doesn't really look like I'm adding the same number every time. But if I want to check, if I thought it was arithmetic, but I wasn't sure what I was adding every time, I would do the exact same thing I did in the previous problem, which is take these terms, and subtract them backwards. So 6.25, for example, minus its previous term. 6.25 minus 1.25, 1.25 is 5. Okay, and then doing it again for the next one, 1.25 minus its previous term, which is 0.25, and I get 1. So you see, it's not the same. When we were doing it in the last problem, we got 0.4 every time. And in this case, I'm not getting the same thing. So it's not arithmetic. I'm not adding the same number every time. So maybe it's geometric, but how do I know? How do I know what number it is I'm multiplying by every time? Because I'm multiplying by some value, and I'm going to call that value r just for now. How do I know what I'm multiplying by? Well, similarly, if you're multiplying gets you moving forward, dividing is a way you can work backwards. So similar to how we subtracted in the last, minute or so when I was looking for arithmetic sequence, if I take these numbers and divide it by its previous term, this can help me identify if it's geometric or not. So 6.25 divided by its previous term, 1.25, is 5. Now let's do that for the next one. 1.25 divided by its previous term, 0.25, I get 5 again. So you see, those numbers are matching. So it turns out, it seems, that geometric is the way to go, that we're really multiplying these numbers. But I'll check the last one just real quick, just to be sure. 0.25 divided by its previous term of 0.05. Oops, I put too many 2's in there. Hold on. Delete. Oh, crap. Delete the wrong one. All right. And I get 5 again. So that tells me that the r value that we're multiplying by is 5 every time. So a way to find that number, like I just did here, the way to find out if you're multiplying by 5 is dividing each term backwards. And if they're all the same, then that tells you you're correct in your pattern. And that our r value is 5. And if you want to check, you can, right? You can start from the beginning, 0.2, or, well, I did that wrong. 0.25 times 5. Oh my gosh, it's so difficult to write on this. 1.25, right? And then do that again. Well, I forgot to start at 0.05, but it's okay. If I take that number and multiply it by 5, I get 6.25. So I'm looking for the next term in the sequence. So if I multiply by 5 again, I'll get the next term. So 6.25 times 5. 6.25 times 5 is 31.25. So the next term in the sequence is 31.25. So now let's look at number 4. Number 4, it's got a fraction in it, which makes it look like it's harder, but it's really not that different. It's going down. Okay, so if it were arithmetic, it would be subtraction every time. And if it's geometric, it's going to be kind of like dividing, but we're going to say multiplying by a fraction. So let's try to figure out what's going on here. Now, I'm going to go ahead and rule out arithmetic, because 18 to 6, if I were subtracting, 18 minus 12 gets me 6. And I know that 6 minus 4 would get me 2. So the fact that I'm subtracting different numbers here tells me that, well, it's not an arithmetic sequence. Because remember, arithmetic would be subtracting or adding the same number every time. So that wasn't the case there. So if I think it's geometric, I'll do what I did in the last problem and divide these going backwards. So here's how you could type this in the calculator, because that is a fraction, but that's fine. We can deal with that. We can use the calculator to use those fractions. If we hit alpha, y equals, right, we got a little menu there. It says the first option is n over d. We can choose that, and it's going to give us a fraction. So we can actually type in 2 over 3. And then we can divide it by its previous term. So 2/3 divided by the previous number, which is 2. And I get 1/3. Okay, which, by the way, I'm going to go ahead and point this out because I think the rest of these are going to be decimals. If you hit math, you see the options. It says arrow fraction and arrow decimal. That's to turn your answer into a fraction.
I found this on the web. I see the option that says arrow fraction, arrow decimal.
Oh my gosh.
Take a look.
What happened there? Am I? Just ignore that. My keyboard is sitting on it. All right. Anyway, apologize. Siri. All right. So that would turn your answer into a fraction or decimal. So since my answer just was a fraction a second ago, if I hit, turn to a decimal, then it's going to turn the 1/3 into a decimal, which is 0.333. And I'm mentioning that to make sure that you understand that 1/3 and 0.33333 are the same thing. So because I'm going to take the next number, like the 2 in my sequence, and I'm going to divide it by its previous term, 2 divided by 6, and I'm going to get 0.33333, which, remember, if you hit math and then arrow to a fraction, just to confirm, that is the same as 1/3. So it's the same thing I got previously. And then one more time, take the 6 and divide it by its previous term, which is 18. And we get, again, 0.33333, which is 1/3. So that tells me that what we're doing here is we're multiplying by 1/3 every time, which, by the way, is technically the same thing as dividing by 3. Multiplying by 1/3 is the same thing as dividing by 3. So you might notice, hey, 18 divided by 3 is 6, 6 divided by 3 is 2, and 2 divided by 3 is 2/3. So what's the next number? Well, I got to take 2/3 and I got to multiply it by 1/3. So I'll just do that in the calculator again. Alpha y equals is my best friend. I'll go ahead and type 2/3 in there. And then I'm multiplying, remember, because even though it's a fraction, we are multiplying that fraction. Multiplying by alpha y equals again. Oops, it didn't hit alpha y equals. Let me quit out of that. Let me get back to this. Times alpha y equals, and then I can type in 1/3. 1/3. And I get 2/9. So that tells me the next number is 2/9. All right. Now let's look at these. Identify the sequence as either arithmetic or geometric or neither. If it's arithmetic, identify the common difference. So what that means is if the pattern is adding, then tell us what we're adding by every time, or subtracting. And if it's geometric, identify the common ratio. So that means if it's a multiplying pattern, what is the number you're multiplying by? Or it could be neither. So let's pay attention to that as well. So looking at number 5, we're going 1 to 8, 8 to 15, and 15 to 22. And again, sometimes it's kind of hard to tell what we're doing every time if we're adding a common value or multiplying by a common value. But if you want to test both theories, you can just work your way backwards. If it's arithmetic, then subtracting the previous term will help you find that out. And if it's geometric, dividing by the previous term will help you find that out. So you're looking for which one of those gives us the same number every time. So let's try arithmetic first. Let's take 22 and subtract its previous term, which is 15, and I get 7. Okay, well, let's take 15. Let's subtract its previous term, which is 8. Oops. And I get 7. And I'll take 8, subtract its previous term, which is 1, and I get 7. So because all of those are the same, that tells me that, hey, this is an arithmetic sequence because my difference is 7 every time. What's going on here is I'm adding 7. Plus 7, plus 7, plus 7. So because we're adding the same thing every time, this would be an arithmetic sequence, or arithmetic, however you want to say it. And our common difference is d equals 7, or we're adding 7 every time. Look at number 6. Number 6 is 0.5 to 2, 2 to 8, 8 to 32. So if I think it's arithmetic, then I'll do what I did before, and I'll subtract the previous numbers. And if they're all the same thing, then it's arithmetic. But if it's not, then I'll try division to test the geometric theory out. So let's try. 32 minus 8 is 24. Okay, what about 8 minus 2? 8 minus 2 is 6. So those numbers are not the same. So it's definitely not arithmetic. So now let's try dividing it. Let's see if it's geometric. If it's geometric, then dividing the previous terms should get me the same thing. So 32 divided by its previous term, 8, I get 4. Okay, what about 8 divided by its previous term, which is 2? 8 divided by 2 is also 4. Okay, well, we're on to something. What about 2 divided by its previous term, 0.5? That is also 4. So because division works, that tells us it's geometric. Geometric. And what we're doing is we're multiplying by 4 every time. And so that's going to be called the R value is 4. So we usually use D when it's an adding number, and we usually use R when it's a multiplying number, just for difference and ratio. It's kind of what they stand for. Let's test number 7. So let's see if it's arithmetic. Let's try that first. So let's take the last number and subtract the previous. 16 minus 9 is 7. 9 minus its previous number, 9 minus 4 is 5. Okay, so I got different numbers there, right? 7 and 5. So it's not arithmetic, because arithmetic would have had the same thing there. So let's test geometric. Let's try dividing these instead. So 16 divided by 9 is 1.778, which is fine. Let's see what I get for 9 divided by 4. 9 divided by 4 is 2.25. So again, different numbers. So it seems that geometric is not working and arithmetic is not working. So this is neither of them. This is neither arithmetic nor geometric. So we'll just write neither. All right. So let's test 8, right? So I'm not sure if it's arithmetic or geometric. So like I said, I'll just take the terms and go backwards. Let's try subtracting first. So let's take negative 23, subtract negative 12. And I get negative 11. Okay. Let's take negative 12 and subtract its previous term, which is negative 1. I get negative 11. So we're on to something. It looks like subtracting works. So this is probably arithmetic, but let's test the last one. Negative 1 minus 10. Also negative 11. So that tells me that, yes, this is arithmetic. And that we're technically adding. Well, it's adding negative 11, but adding negative 11 is kind of like subtracting 11. So what's going on is we're subtracting 11 every single time to get one from one term to the other. And lastly, number 9. So it doesn't look, just by the look of it, it doesn't really look arithmetic, because we get that fraction out of nowhere. So I'm going to test geometric first. So I'm going to take my alpha y equals to type in this fraction. So 4 over 5, and then divide it by its previous term. So I'm testing geometric. So I'm going to divide these all backwards just to see what the value is. So 4/5 divided by 4 is 1/5. So I want to keep that number in mind, which, by the way, just to let you know, if we hit math and I turn it into a decimal, so arrow decimal, 1/5 is the same as 0.2. And I'm saying that now because we're going to probably get decimals later on. So let's take 4 and divide it by its previous term, 4 divided by 20. And we got 0.2, right? So that's the same thing as 1/5. And if we take 20 divided by its previous term, 100, we get 0.2 again. So because division was what worked here, this is a geometric sequence, meaning that we're multiplying by 0.2 every time. Okay. So remember, when I'm doing subtraction from one term to the next, or I'm doing division from one term to the next, going backwards, that's only to test a theory to help me figure out if it's arithmetic or geometric. But at the end of the day, that is still backwards. So yes, I was dividing and I got 0.2, but that was only to tell me that really I'm multiplying by 0.2 to go forward. And again, to test that theory out, you could plug that in. 100 times 0.2 is 20. 20 times 0.2 is 4. 4 times 0.2 is 0.8, which 0.8 is the same thing as 4/5, by the way, right? If you hit math and then turn to a fraction, that 0.8 is 4/5. So when I do it backwards, it's only to figure out which sequence works, and then that number will tell me what I'm adding by or multiplying by, depending if it's geometric or arithmetic. All right, so write an explicit formula for each sequence. So there are 2 formulas that you need to know. AN equals A1 plus D n minus 1. This is my arithmetic formula. I'm just going to call A for arithmetic. And then there's the geometric formula. Geometric formula is an equals a1 r to the n minus 1 power. So really, all that we're going to need here, I don't know if I can change colors. I don't think I can change colors. It'd be nice, but I think we're good. Now, a1 on both of these just means the first term. So whatever the first term in my sequence is, that number is going to go there in the formula. And then D and R are kind of similar. If you look before, oh, I forgot to mention it. The D value here is negative 11 because we're subtracting 11. And the R value here is 0.2. So those are the D and the R values, kind of what the difference in the sequence is. So if it's an arithmetic sequence, you know, D is the number you're adding by every time or subtracting by every time. If it's a geometric sequence, R is the number you're multiplying by every time. So remember these formulas, jot them down if you need to, but I'll write them again and again and again as we go throughout this. So all we're doing is using those formulas kind of as a template. We find those two values, we plug them into the formula, and then we have our formula for that sequence. So notice this sequence, 51, 57, 63, and 69. If you're wondering if it's arithmetic or geometric, do the same thing that we were doing before to determine that. I'm going to go ahead, just to save time, and tell you that this is an arithmetic sequence. So we're going to use the arithmetic formula, which is this one that I just wrote down a second ago. And all I need is the first term and the difference that we're adding by. So the formula for this problem, the first term is 51. So 51 will go right there for the first term. And now I'm adding, everything here is adding 6, plus 6, plus 6, plus 6. So that's the number I'm going to put where D is. And then I'm going to have that parenthesis n minus 1. That's just part of the formula. It's just these two numbers that we need. Now the purpose of this formula that we'll use later on is if I want to find, let's say, so this is the first, second, third, and fourth term, right? But let's say I wanted to find the 51st term in the sequence. Well, I don't want to have to write out all 51 terms, right? That's what the n here is for. If I put 51 in for this n, then I can calculate this whole thing, and it will tell me what the 51st term is, which is nice. I don't have to list them all out. So that's the purpose of this formula, but we're not actually looking to find the 51st term right now. I just want to make sure that we can write the formula. So number 11. Number 11, again, you need to first identify if it's arithmetic or geometric, and you can do that the same way that we did up here, which is subtract backwards or divide backwards and see which one, works out. I'm going to go ahead and tell you that this is geometric. An equals a1 r to the n minus 1 power. So this is the geometric formula we wrote down a second ago. So all I'm going to do is from this sequence, identify the first term, which the first term is 0.3. So an equals 0.3, and just use that right there for my first term. And then r is a number that we're multiplying by. So if you divide it backwards, 19.2 divided by 4.8, 4.8 divided by 1.2, 1.2 divided by 0.3, you would find that the r value is 4, that we're multiplying by 4 every time. So since we're multiplying by 4 every time, that is the number that goes there. And then n minus 1 is just part of the exponent. So similarly, if I want to find the 51st term of this sequence, I would put 51 in for n and calculate it out, and it would give me my 51st term. But of course, that's not what I'm trying to do right now. All right. Number 12 is a little funny. If you're working backwards, if you subtract these, arithmetic will not work. If you divide them, it will. Now, it is a fraction. So in the calculator, if you get a decimal, which you probably will, I would like for you to change it into a fraction. So for example, you would test 20 divided by its previous term, which is 30, and you would get 0.666666667, right? And you can take 30 and divide it by its previous term, 45, and you get the same thing, right? And if you do 45 divided by 67.5, you get, again, the same thing, but they're all decimals. So what's the fraction, right? Well, remember, hit math, and you can see you can change it to a fraction. So hit enter on that fraction, and it will change it to a fraction. So 2/3. 2/3 is the number we're multiplying by. And I know that because, like I said, you can do the division to find that number. So it's geometric, same formula as before, and the first term is 67.5, so 67.5 will go here. And then the r value is that 2/3 that we're multiplying by, to the n minus 1 power. All right, and number 13, I'll go ahead and tell you this is an arithmetic sequence. an equals a1 plus d n minus 1. Arithmetic, this is the formula for arithmetic again. We wrote it down earlier. So I just need the first term and the difference. So the first term is -8, so -8. And then the difference is kind of funny because I'm actually subtracting. I'm going down, I'm subtracting 3 every time here. So I'm going to put -3 there for that. And then n minus 1. All right. I know this is getting really, really long, and I apologize, but I want to be thorough. Number 14, what is the 17th term of the sequence? So 14 and 15 are pretty much the same as all of these problems down here that we just did, except now we're actually going to plug in a number for n. So number 14, it looks like my pattern is +5, +5, +5. All right, well, if the pattern is +5, then that's an arithmetic sequence. So I'm going to use my arithmetic formula, make this first, and then I'm going to plug 17 in for n to find the 17th term. So an equals a1. a1 is 13. My difference, I'm adding 5 every time, so +5. And then, because I'm looking for the 17th term, I'm going to plug 17 in for n, so 17 minus 1. And I could just type that in the calculator exactly like this, and the calculator will tell me the 17th term. And I believe it's 93, but I don't remember exactly. You might want to check for yourself. So what is the 9th term of this sequence? Now, looking at this pattern, if you can't tell, right, it looks like you're multiplying by 2. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. So since we're multiplying, this is a geometric sequence. So this is my geometric sequence formula. And again, let's plug in all these values. So a1 is the first term. The first term is 6. R is what you're multiplying by. So we're multiplying by 2 every time here. So 2. And then n. N is 9 because we're looking for the 9th term. So 9 minus 1 as the exponent, which you can write as 8. 2 to the 8th power, because 9 minus 1 is 8, right? And then that calculates that. Just type that in the calculator exactly like it, and you'll get your 9th term. All right. So find the first 5 terms of the sequence. Number 16. So number 16, we already know the first term is 14. So I'm going to list these out over here. So the first term is 14. It tells me that right there. Now what this formula says here, when you see a n minus 1, you're going to see it here as well in the next problem. A n minus 1, that whole thing means previous term. I'm just going to write prev for previous. Okay? You're not plugging in for a or for n. You're plugging in for this entire square, this entire thing. That an minus 1, that whole thing just means previous term. So if you want to find the second term, right, the second term, then you have to plug in the previous term, which is 14, to this space. So that means the second term would be 14, and I'm going to put it in a square because I put this in a square. 14 plus 3. So whenever you see that an minus 1, you have to replace that entire space with the previous term. So the second term, 14 plus 3, is 17, so the second term is 17. So now, if you want to find the third term, you have to plug in the previous term, which was 17. So I'm going to put 17 in that space now. So it's going to be 17 plus 3. 17 plus 3 is 20. And if I want to find the term after that, I ran out of space there. If I want to find the term after that, I plug in its previous term. So I'm going to plug in 20 into this space now. So it'll be 20 plus 3. 20 plus 3 is 23. And then you do that one more time and you get 26. And that finishes the sequence. So number 17, again, same thing. I put a little box around it to say previous term. So this is going to be 2 times the previous term and then add 5. So let's write down our sequence blanks. So the first term is already -2. I know that. It tells me that right here. So that means if I want to find the second term, I'm going to plug in the previous term, which is -2. So in that box, I'm going to write -2. So what this says is it's 2, and I'm going to put parentheses here, 2 times -2 plus 5, which again, just type that out in the calculator, and I believe it's 1. Okay, so if that's 1, then to find the next term, the third term, I plug in 1. So in that space, I'm plugging in 1. I'm not plugging in for A or for N or anything like that, remember. I'm plugging in for this entire thing. This entire thing is 1. So it's going to be 2 times 1 plus 5. And again, type that in the calculator, you get 7. I'll let you finish the rest. The next time you have to plug in 7, and then the time after that, you plug in whatever you get as the fourth term. Okay? You just keep plugging in the term you get to get the next term. So now, write an equation that represents a formula for an arithmetic sequence. So it's telling us an arithmetic sequence, so I know the formula for my answer will be in this format. But of course, I need to know A1, which is the first term, and I need to know the difference D. Now, it's easy here because I know that the first term is 7. So my formula is, I know is AN equals 7 plus, but I don't know what this D value is yet. I know I'm going to leave n minus 1 alone because remember, it's just like these problems over here where I was just trying to write the formula. So I didn't really plug anything for n. I'm not going to plug anything for n unless it asks me a certain term like it does here. That's when I plug in those numbers for n. But it's not asking me for that. It's just asking me for the equation, right? So I'm going to leave the n alone. But I do need to figure out what d is. So I know the first term is 7. It's given to me here. But how do I find d? Well, because this is an arithmetic sequence, right? The first term is 7. Then I have the second term, the third term, the fourth term, the fifth term, the sixth term, the seventh term, and the eighth term is 35. So because it's arithmetic, that means I'm adding the same number every single time. The same exact number every single time. Knowing that, I'm going to make this equation. Okay, so follow along. We're starting at 7 now, right? So I'm going to write down 7. And then I'm adding the same number 7 more times because from the first term to the 8th term, from 1 to 8, that is 7. So you see 1, 2, 3, 4, 5, 6, 7. So I'm adding some number, which I'm just going to call D, 7 times. So that could be, 7 plus D plus D plus D plus D, and you can have that 7 times. But an easier way of writing that is 7D. So this is saying, hey, we're starting with the number 7, and then I'm adding another number 7 times, and I get to, as a result, 35. So all I have to do is solve this equation now, and I find for D to find out what D is. So subtract 7. That's going to be 7D equals 28. And then divide by 7. 28 divided by 7 is 4. So D equals 4. So plug it in, and I've got my equation. All right, now number 19 is very much the same thing as basically the very, very first problem we did today in this video. The cost of piano lessons is given in this table. So 1 hour is $11.50, 2 hours is $15, and $3 is $18.50. So my goal is to figure out, hey, what kind of pattern do I see here? And does it continue so that I can predict what will be 4 hours cost? Because it's asking what will a 4-hour lesson be. So let's see if we can identify a pattern. So if I think that it's an arithmetic pattern, that I'm adding something every time, then I can work backwards by subtracting. Let's take 1850 and subtract its previous term. So 18, oops, I hate it when that happens. I don't want to full screen it. 1850, subtract its previous term, which is $15, and it's 3.5. Okay, that's 3.5 between these. But let's test the other one. Let's test $15, subtract its previous, which is $11.50, and I get 3.5 again. Okay, so I'm adding 3.5 every time. It's $3.50 more for every single hour. So if I do one more hour, then I need to add another $3.50. So $18.50 plus another $3.50, whatever that number is our total cost for piano lessons. And that's going to be it for the video. Apologize if it took too long, but again, I want to be very, very thorough. So I hope it helped. Let me know if you have any other questions, all right? I'll see you later. Bye.